Dear friends, this is my tutorial 35. So in this tutorial you can learn how to perform electrochemical CO2 reaction calculation in VASP. Okay, so this is the TOC figure. So here what's happening, CO2 molecule react with the 2 electron and 2 proton will form the one equivalent of a CO molecule plus one equivalent of water molecule. Okay, this is the 2 electron pathway. Okay, this is the graphene and this is the palladium supported single atom catalyst. Okay, so this is the actually mechanism for the conversion of CO2 to CO molecule. Okay, so first step you can see here, this is the catalyst. This is the catalyst react with the CO2 plus one electron and proton, it will form so COOH intermediates. This is the first intermediate. Then another equivalent of proton and electron react with this one will lead to give one equivalent of water molecule plus one equivalent of CO will absorbed on the active site. So final step is desorption of the absorbed CO. Okay, so then the CO plus water molecule will formed. Okay, this is the energy profile for CO2 electroreduction. Okay, this is actually CO2 to CO formation. Okay, there are different kind of mechanism also, is the formation of methane and also ethylene and also ethanol and methanol kind of things. So you can read one of my paper, I will show you in the tutorial. You can understand how to do the whole mechanism. Okay, so this is my paper. Actually I used MO2 CS2 MX in supported single atom catalyst for efficient and selective CO2 electrochemical reduction. Okay, so this is the one. You can read also how I did in computational details. You can get how I calculated for neta and limiting potential and all. So this is the system actually I used for my studies. Okay, so here also see I have studied that comparative plot for Gibbs free energy for first protonation, step in CO2 electroreduction and hydrogen evaluation reactions. Okay, we need to study this kind of things, that then only we will get the our catalyst CO2 selective or HER selective. Okay, from there we can separate the HER selective catalyst and we will use only the CO2 or selective catalyst for further studies. Okay, so then I studied that binding energy calculation for the transition metal disease. So this is the mechanistic pathway. Okay, you can see I have calculated a different kind of mechanistic pathway in order to produce methane. So here you can see methane formation, methanol, and also you can see here CO and formic acid. Okay, these are the different kind of product if you do this CO2 electroreduction. Okay, so this is the important optimized geometry I have mentioned in this paper. You can also read it, this you can understand easily. Okay, yeah, this is the constructed energy profile. You can see how I constructed. You can also make it like this. So here also you can read this paper and also see the table 1 for you can identify the potential determining step. Okay, so that's all. So now I will tell you what are the important things need to do for CO2 electrochemical reactions. Okay, so this is the in order to do your CO2 electrochemical reactions you need your catalyst. Okay, this is the catalyst. So I will show you using this Vesta. So you need to optimize your catalyst. Okay, this is the catalyst. Then you need to optimize your COOH intermediate. Okay, so this is COOH intermediate. So then you can also optimize CO intermediate, CO absorbed intermediate, but nickel it won't interact strongly with that CO, that's why it's showing like this. Okay, if you use iron it will strongly interact with this one. Okay, so then you need to also calculate the hydrogen absorption. So because we need to calculate the hydrogen binding energy in order to check the selectivity. Okay, is the HER selective or CO2 RR selective? Okay, so already I made several videos how to do optimization and how to do frequency calculation and all. After completion of this one, I have made several video on this how to do optimization. Okay, just follow that earlier video to do your optimization and make like this kind of absorption structures. Okay, then optimize, then you do the frequency calculation. So I already made one more video also, the frequency calculation. Just you can check that my earlier video. You can do the frequency calculation of this absorbed intermediate. Okay, so after absorption on this calculation you can get from 0 point energy entropy. Okay, I already made that how to get your entropy and 0 point energy for absorbed species and also gas phase. Just watch other videos, so then you will get your 0 point energy and entropy. Okay, now I will tell you how to get your energies. Okay, I will tell you this one. Just to go to VASP log. This is the VASP log file. Otherwise you can also go to OCR file. Okay, you can see this two file, you can get your energy. Okay, I will show you from that VASP log file. So this is the VASP log file. If you go down, you will get here E0. This is the your energy of this system. Actually this is the system is nickel COH intermediate. Okay, so here that is 674.98431. this is because of 0.3, that's why I mentioned 674.98. okay, so you can copy this value, you can paste it your table. Okay, so likewise you can check this all intermediate and take your optimization energy. Okay, so then what you have to do, so now I will tell you how to calculate. So I took these energies I have mentioned, kept here. You can see this is the pure catalyst energy, this is your absorption COH absorption energy, this is CO energy, this is the nickel H energy. So I also took that 0 point energy and T del S from the my frequency calculation. So then I subtracted this value from the total value, then I added this value to this one. I got this the final G value. Okay, so then you need to also optimize your small molecule, that is H2 and H2O CO CO2. Okay, this is for small molecules are very important in order to calculate the CO2 reduction reaction. So these are the DFT energies. Okay, you need to do. So to optimize H2 I have made one more video also for this especially, so you can follow that video how to optimize H2 molecule. Okay, that's all. Then you have to do the 0 point energy correction and T del S correction for small molecule. So I also made some videos for this one, how to correct 0 point energy and T del S from the total energy. Okay, small molecule energy. So this is the, you can check with the frequency. This is actually experimental 0 point energy and entropy. Okay, so this is the calculation method, just to follow this one. So actually this is the 0 point energy of a H2 molecule, this is the entropy of the H2 molecule. Just you can substitute this value into your calculator, then you will get, this is the final G values. Okay, this is 6.89026. this is the hydrogen energy value. Okay, this is actually half of the H2, just I divided by 2, I got this one. Then like that you also calculate CO2 also. For CO2 this is the DFT optimization energy, so this is the 0 point energy, this is entropy. Okay, after you substitute this value into a calculator you will get this one. So likewise CO2, CO and H2 also you can calculate. Okay, then you will get the, this is the final energy for the small molecules. Okay, So after getting this energy, just you need to calculate the CO2 reaction mechanism. Okay, this is the step 1. So first step, what is this? COH formation. Okay, for first you need to calculate the step 1. So this is the COH formation energy. So here you can see that star COH means COH absorbed on the active site. Okay, this is actually catalyst. Star means catalyst. Then you have to take CO2 energy off of H, of H2. Okay, of H2 you have to take. So I will show you this energy 674. This is actually this energy. Now we have to see in the table. Okay, so this is the COH energy. Here you can see 674596074. So I also mentioned this energy. Then you can add this 3 energy, you will get this one. So what are the energy you need to add? So this energy, catalyst energy, and you come here and you can take this off of H energy. Okay, then CO2 energy. So this is the CO2 G value. Okay, G energy. You have to take this 3 and add it and put it here. Just you can use calculator to calculate this one. So click, you will get 1.80. Okay, 1.80 means, so 1.806, I round up to 1.81. okay, this is the first step. Then you need to calculate the formation of CO. Okay, this is second step. This is the second proton and electron addition step. Okay, here you have to take the CO absorbed system plus water molecule. In this step, one water molecule will form, so we need to add that energy. Okay, that is very important. Okay, then you need to add the same energy only. Yeah, here is not same energy, just we need to, here only we added the of H2. So here we are adding one equivalent of H2. So if you add this H2 energy, CO2, that intermediate, you will get this energy. Okay, then you can substitute this energy into that calculator. .91. Okay, this is the your second CO formation energy. Okay, so then the final desorption energy is different. I will tell you the later. Then you have to calculate your H absorption energy. Okay, so first you need to calculate that H absorption energy. So simply you can subtract with that hydrogen absorbed system, the catalyst, so half of H2. Okay, so half of H2. Okay, half H2 you can take directly. This is the E value you have to take, not G value. Okay, so this is that hydrogen absorbed system energy. This is 651.60953. so this value. Okay, this value you have to take. Then you have to take off of the, this is that pure energy, so you have to take off of this one. Okay, for H absorption calculation. So that's very important. You take that one and you can subtract this 2 value. This is the product, this is the reactant. Okay, you need to understand that. Then you will get so 1.39 you will get positive energy. So you can substitute into that. Okay, see 1.39. okay, this is the, I think this is the very weak absorption. Okay, that's why we are getting 1.39. so second step only we have to calculate the G value, delta G value. This is the E value. Now we will calculate delta G value. So I also already made 2 or 3 videos, so how to calculate that hydrogen absorption energy. You can also watch that video. So actually experimental 0 point energy of H2 is 0.27. actually you can see here. You will find this. So H2, this is the 0.27. that's why I'm mentioning 0.27 here. So then the calculated 0 point energy of H atom is 0.167515. so you have to take from your vibrational frequency calculation. Okay, so this is the 0 point energy of that one. Okay, that hydrogen absorbed system. So then you need to subtract with the half of 0 point energy of H2. Just you can subtract these two and you will get this is the 0 point energy of the absorbed system. Okay, then we need to see the entropy of the absorbed H. Okay, so entropy of the absorbed species almost you will get 0 only. So if you go to the table, you can see this around 0.01. okay, this around 0. Okay, that's why we need to take from the experimental entropy. Okay, so here experimental TDLS H2 is 40. Okay, 40. The half of the things is 200. Okay, we need to use this value. So then you can take your 0 point energy minus T del S. Likewise, you will get this value. This is the very important value. Okay, this is the corresponding to this value. Okay, we need this value in order to get delta G H. Okay, so then finally you need to substitute this value into here and here that what you got here delta E value. Delta E here you substitute this value from here, then you can use your calculator to get energy. So just to substitute, you will get 1.62. so see, this is the very weak absorption. Okay, so likewise you can calculate your CO2 RR mechanism and hydrogen absorption for the CO2 electrochemical reduction reaction. Okay, so then we will plot the graph. Okay, it's very simple only. So this is the open your origin plot. So I plotted. Just you put your energies. First you can put 1 equal to 0, that is the 0.0 we will start. Then you can put the second value 1.81, that is COOH formation. Then second one is third one is the CO formation. Okay, fourth one is 0.12. This is actually equilibrium potential for the CO2 to CO formation. We need to use this value only. If you see some papers, they always use this value only. I will show you that paper. So not this one. So this, if you see this paper, they will always put this value here only 0. This is actually 0.12. Okay, you will find this. So every paper they will use this value only, equilibrium potential for CO2 to CO conversion. That's why I also used same value. I will also show other papers. Yeah, this paper they did not show anything. So yeah, you can also see this paper. This is actually nickel N4C. So you can see this is actually 0.24. Okay, 0.12. Okay, this is the value. So they also calculated the nickel N4C. See, this is the around what we got, that 1.83 we got. There they also got 1.67 something. Okay, so similarly we also got, and also they calculated the H absorption on nickel N4C. So they also got around we got 1.62 something. They also got 1.70 kind of thing. So our calculated value and this value also is more or less equal. Okay, so you can see these two papers, you will get a more idea. Okay, then we will see the plotting of this one, this graph. Just you can select this one, just plot it. Scattering, I already mentioned many videos, so just you can also plot like this, you will get, and that's okay. I think you can plot easily. So you can see the first step. This is the formation of COOH intermediate. I mentioned here, this is CO2 with one proton and electron, it will form this. Second one, take one more proton and electron, it will form CO intermediate. Then finally it will release CO plus H2O. This is 0.12. Okay. That's all. So then you can save this image and you can use it for your research purpose. Okay. Thank you for watching. If you like my content, please like, subscribe, comment and share, and also please click the bell icon on future videos. Thank you for watching. Enjoy.